Hello, everyone. Thank you for joining us today. We've got a great audience here in the room with us, and I'd like to welcome all of you joining us remotely as well. This session is session number N33A, and the PDH code is 24423. The name of the session is Is It Likely My Designs Will Fail? Now, actually, this is a lecture that's given by a past Higgins Award winner who is giving another lecture to follow up his Higgins Award lecture, maybe some other lectures he's given in between as well. The presenter's name is Ron Hamburger, and I will give his bio a little bit later, but I gave you the PDH codes. My name is Larry Caruth. I'm from AISC, and I'll be moderating today's presentation. Got a couple quick announcements for you. To obtain PDHs, you'll need to visit www.aisc.org/NASCCPDH, or you can do this from your mobile device or any computer or from the station set up on level 300 in the convention center. For this presentation, the speaker will address questions at the end of the session, and due to time constraints, we'll see how many he'll be able to answer. For those of you in the room with us, simply raise your hand and with any questions. For the remote audience, you'll find instructions for submitting questions, including on the viewing page. Now, I'd like to introduce today's speaker. His name is Ron Hamburger. Ron is a senior principal at Simpson Gumpertz Hager, has more than 40 years of experience in design, construction, engineering, failure investigation, and teaching. He is an internationally recognized expert on performance-based engineering with particular emphasis on seismic. He's former chair of AISC's Connection Pre-Qualification Review Committee, a member of the Committee on Specifications, and chair of the ASCE 7 Committee. I'll turn it over to Ron.
Thank you, Larry, and good evening, everyone. Yeah, I probably won't need that, but thank you. About 9 months ago, Larry asked me if I would do a presentation at the conference. He mentioned that it was going to be an invited lecture that they're doing, making available as options for former Higgins lecturers, and he said I could pick any topic I wanted. And I thought about it for a while and decided that in the last few years, what I've really become interested in is probability of failure and dealing with the question how likely it is that a structure we design will fail. And so that's what I'm going to talk about this evening. Is it likely my design will fail? And I'm going to be talking about, in particular, when you go through and you evaluate your design and you find, or you evaluate an existing structure, and you find that the demand capacity ratio exceeds 1, and you want to know, is that okay? And for many of us, I'm sure probably all of us in the room at some point have done a calculation. We've come up with a demand capacity ratio of 1.05, and we've scrolled at the bottom of our calc sheet, say okay. And so a subtitle here is, we say it's okay, is it really? And another subtitle is Fun and Games with LRFD, which is really what my talk is actually about. So I'd like to start, given that it's based on LRFD, with some acknowledgments of the gentleman that brought LRFD to design practice, notably Bruce Ellingwood, who in the summer, I believe it was, of 1977, called together at the National Bureau of Standards something that he called his summer camp. And he invited a limited number of people to his summer camp. One of them was Dr. Alan Cornell, another Ted Galambos, and finally Jim McGregor. Jim was invited from Canada, where he had helped to develop ultimate strength design, which was concrete industry's version of LRFD that they actually developed earlier than the steel industry did. He invited Ted to represent the steel industry and Alan Cornell to represent earthquake engineering. And they put together the framework that became LRFD as we know it today. They never intended it to go to the places I'm going to take you today. In fact, in the early 1980s, Ted Galambos wrote a paper to introduce LRFD concepts to the steel design profession, and he had words in it that said, not exactly, kids, don't do this at home. Hopefully he won't be too mad at me. All right, so a common problem, as I said, you do a diligent job in design. You design your structure, everything meets the code checks. After it goes into fabrication, for whatever reason, you're told that the load is going to be larger than you originally designed the structure for. Maybe an elevator vendor decided that they're going to use a new type of car that weighs more. Maybe the architect has decided he wants to design the room for some other occupancy. But for whatever reason, you're suddenly faced with the load is more than I designed for. You go through, you do a check, and your DCR is greater than 1, and you say at the bottom of the page that, well, it's okay. And in this case, in this example, I'm going to use our demand capacity ratio is 1.07. You decide that it's okay. And the question I want to play with a little bit is, should I really say it's okay or not? And what risks am I running if I say it is okay? And give you a way to use the basis of load and resistance factor design to help you make that judgment. All right. So first of all, I'm sure that everyone in the room and online as well saw at some point in their education, either before going into practice or after, this very common diagram that you see here of two probability distributions. One represents the probability of experiencing loads or demands of given levels, shown in blue here. The other is the probability that your resistance will exceed a certain level, shown in orange here. And you were told, I'm sure, either in the papers or by your professor at the time, that the overlap of those two curves represents the probability of failure, and that we try to separate the resistance distribution on the one side and the demand distribution on the other side, so that the probable load effect is going to be less than the probable resistance at a high confidence level, so that our structures don't fail and people don't sue us. Now, in reality, this figure that I'm sure you were shown, and maybe you saw one that was even worse than this, if your figure looked like this and your overlap of your load and resistance curves looked about like shown in this figure, your actual annual probability of failure would be about 10%. So the real picture is actually much different than this. All right, this is the figure they showed you in school. This is what we really look like if we have a demand capacity ratio of 1, and we're following ASCE 7, and we're following the specification. The intended probability of failure is very small because we hate when our structures fail. We could show up, as Dwayne Miller said in a session I was just in, on the cover of ENR in not a good way. Not good for our reputation, maybe not good for our wallet. So what are the probabilities of failure that we design for? For many, many years, no one really knew unless they did research looking into arcane papers that were buried back in the 1960s and 70s. A few years ago, we brought into ASCE 7 commentary describing what the intended probability of failure is if you use the load combinations that are contained in the standard and you actually design with a DCR of 1 or less. And the probability of failure depends on a couple of things. 1, the type of loading you're looking at. 2, the risk category for your structure and how conservative we want to be. And 3, the type of failure or limit state in classic load and resistance factor technology that we're dealing with. And these range from limit states, failure mechanisms that develop slowly as you apply load to a structure, give lots of warning that they're going to occur. For example, the failure of a simply supported steel beam as you put load on it, before it actually developed the plastic hinge in the middle, the limit state we're protecting against, it would start to sag a lot and give warning that it's going to occur. And if you were paying attention, you might stop loading it at that point. If you didn't pay attention and you continued to load it and you actually got the plastic hinge forming, probably the floor wouldn't collapse, it would just sag a whole lot more. So lots of warning, not a horrible effect. At the other end of the spectrum, we have failures that occur suddenly without any warning and cause a whole lot of damage when they occur. And an example of that might be a reinforced concrete column that suddenly takes on too much axial load. You might actually crush the concrete. The column would shorten, and if there's not a way in the structure to redistribute load from that column to other columns, you could actually cause collapse of the structure. Now, as you know from your practice, we assign resistance factors of different levels to different types of structural elements and for different modes of behavior, shear versus flexure versus axial load. And what those different resistance factors is all about, basically, is how benign or dangerous we view the failure mode is in the particular thing you're designing for, and how much warning you're going to get that it's going to occur. But let's talk about our most benign situation, a steel beam loaded in flexure that's going to form a plastic hinge in the middle. If you design that steel beam for dead and live load, and you design it so that it has a demand capacity ratio of exactly 1, what is your annual probability of failure? Well, tables that are in Chapter 1 of ASCE 7 would tell us that if you do that, you design for dead and live load for a simply supported steel beam, and you have a demand capacity ratio of 1.0, the annual probability of failure for that beam is something on the order of 3 times 10 to the minus fifth. Not very large. So we shouldn't see many failures, and we don't. Of course, if you've been practicing a number of years, as I have and a few others in the room have, you've designed a whole lot of beams. And if you add all of those beams up, the probability that one of those beams will fail starts to grow significantly more than that, which is one of the reasons why we keep these numbers pretty low. All right. Now, there's a number of reasons or a number of ways where we get to this probability of failure being very low. First of all, our design load is usually much larger than the average load, and I'm talking before we put load factors on it. Our actual design load is much larger than the load we actually typically have in place on a floor system. So, if you look in ASCE 7, you can find hints to this. For example, in one of the seismic chapters in ASCE 7, where it's looking at extreme loading from seismic, and it tells you what load to assume from dead and live, it tells you actually only to use 50% of the design live loading, because that's the loading that's actually likely to be present at any point in time or when the earthquake actually occurs. So we have our design load specified here. Maybe it's 100 pounds per square foot or 60 pounds per square foot, depending what our occupancy is. But if you were to do a survey of the actual loading present in the room at any point in time, you would find it's much lower than that. So in reality, our codes have built into them a load effect bias, where the load that the standards tell you to design for is much larger than will usually be present. Not much larger than can be present, but much larger than usually present. Our required resistance is set to meet or exceed the factored load by a large amount. So we start with our specified design load, which is larger than we're typically going to have present. We factor that up by a load factor to provide additional safety. And then we require that our resistance, as long as our demand capacity ratio is greater than 1, is in excess of that factored load effect, right? And we do this in a couple of ways. One, we apply a resistance factor to our elements. And the other is we recognize that we're calculating our capacity using specified values of material strength, and that the actual values of material strength are likely to be significant in excess of that. So we throw a resistance factor of 0.9 on our elements. That gives us another 10% resistance above this factored load effect. And then if we're specifying A572 steel, which has a specified yield strength of 50 KSI, the actual steel member may have a yield stress of 58 or 60 KSI. And so there's another 20, 30% of beef, if you will, in our design. Now we account for this, well, we don't, but the people who write the specifications account for all of this by developing load and resistance factors. And in commentary to Chapter 2 of ASCE 7 now, you can see a description of how these load and resistance factors are actually calculated. They use the formula that you see here on this slide, and I'll break them down a little bit for you. In each of the formula, you have a term that compares the mean value of the load or resistance to the specified value of the load or resistance, and that's taking care of this bias, the fact that the specified load on one side is going to be larger than what the actual loading is likely to be, and the fact that the specified resistance on the other side is likely to be less than the actual resistance of the member that you're designing. So that's a matter of bias. Then the second term in there, the exponential term, takes care of that probability distribution that you saw in those bell-shaped curves, and that relates to how many standard deviations above or below the mean we want our design point to be. And the specification writers adjust that number of standard deviations above or below the mean with a factor that they call beta, or a reliability coefficient or index, which is typically on the order of 3 or 4 or 5. Now, some of you may be familiar with some of the quality assurance procedures that have been published in recent years. The military has had a program for a number of years where they talk about 6 sigma, meaning they want things to be highly reliable. That 6 is the reliability coefficient. By the way, 6 sigma is ridiculous. No one can produce 6 sigma. It's a nice buzzword. It says we want things to be really safe, but it doesn't exist. All right, so if you understand that, sort of, there's some cool stuff you can do with this. One is you can modify the load factors that you're using in your load combinations if you understand that there is good control on what the load might actually be in your structure. All right, so there's a difference in the amount of load that might go into a room like this. Depends on the number of people that are put in it, depends on whether exhibitors are likely to bring heavy stuff into it for trade shows. There's not a lot of control on how much load goes into this room. On the other hand, if you're designing a structure that holds up a tank or a bin, and you know the owner of that structure is only going to put one material in it, and you know that the material you can't get more material in the bin than what the volume of the bin is, you have a totally different situation in terms of what the potential variability of the load is. So if you're going through and you do a design and you find out that you suddenly have large DCRs and you're worried about that, and you know you're in a situation where the amount of load that can be placed on the structure can be and will be carefully controlled and limited, you can go into the load combinations and play with the load factors using the equations I showed you on the previous slide, and maybe get your DCR back down to 1 or less. If you're working for someone that has a new, better idea about a new material or a new system that they want to use, and there's no current specification that controls the design of that, they can use this theory to develop the resistance factors that they put into the specification for how to design it. But that's not what I'm here to talk to you about today. What I'm here to talk to you about today is how to figure out the probability of failure if you have a demand-capacity ratio that's greater than 1. And I first started playing with this in this way about 2 years ago. Our firm had a project working for the US government. They decided that they wanted to put Osprey tilt-rotor aircraft onto the Pentagon's helipad. The Pentagon's helipad wasn't actually designed for the Osprey. Osprey is a much larger aircraft, much heavier. We knew that we were going to calculate demand-capacity ratios greater than 1 for this structure. And we wanted to come up with a way to help the client understand what the risk of landing this aircraft on that helipad would be if they didn't go and reinforce the structure, which they didn't really want to do. So I developed the procedure that I'm going to tell you about now. So first, let's start with a reliability theorem. I will tell you that load and resistance factor design has 2 inherent assumptions. They're not completely appropriate, but nevertheless, that's what's used. And these are that the load, the probability around what loading you might have on a structure, can be represented by a log normal distribution that has a median value. It's not necessarily a specified value, but it has a median value, and it also has an uncertainty or standard deviation, you can think of it, associated with it that I'm going to represent by the symbol V sub Q for variability in demand. Resistance can similarly be represented by a log normal distribution having a median value and also a variability associated with it that we'll call V sub R. So, if you can represent load and resistance with log normal distributions having independent variabilities, V sub Q and V sub R, Then you can represent demand to capacity ratio with a similar log normal distribution, having a median value equal to the median of the demand over the median of the resistance, and having a variability that's given the sum of the square root of the sum of the squares of the variability in demand and the variability in resistance. And if you have a known probability of failure, when your demand capacity ratio is 1, then you can compute with knowledge of that known probability of failure and knowledge of that variability of demand and resistance, what the probability of failure is at any demand capacity ratio that you happen to find your structure is subjected to. And that's what I'm going to teach you to do. All right. So where do you find the probability of failure for your structure? Well, you find it in ASCE 7, either ASCE 710 or ASCE 716, table 1.3.1 or 1.3.2 if you're looking at seismic loads. And as I said, it depends on the risk category, the mode of failure. And I do want to point out that these probabilities are not real, they're notional. And the reason they're notional rather than real is because the people that wrote the specifications, when they came up with the resistance factors and the load factors, they rounded things off. They might compute that the load factor on live load should be 1.37, and they said, well, we don't want to use that. Let's use 1.4. And they might have computed that the resistance factor on a particular type of structural element, let's say in shear, should really be 0.73, and they say, oh, gee, if we do that, it's going to take an awful lot of material. Maybe we'll cheat a little bit and call it 0.8. So sometimes it was conservative cheating, sometimes it was unconservative cheating. At any rate, these probabilities of failure are not exact. Okay? They're notional. So what is the approximate procedure to determine the probability of failure if you believe that the design specifications will actually give you the probability of failures stated in ASCE 7? And you have to adopt that as an assumption. One, first step, you determine the probability of failure for the element that you're interested in, for the risk category and failure mode that you're worried about. All right? So you go into ASCE 7, table 1.3.1, and you find what the target probability of failure is, given that you have a demand capacity ratio of 1. Next, you estimate your dispersion. Now, I know you're all sitting there saying, well, how can I estimate dispersion? Well, the fact is, other people have estimated that dispersion, and it is documented, and it is out there. And if you dig around in the right places, you can find it. I've got it in these slides, and after, I haven't talked to Larry about this, but if he'd like, I'm more than happy to make these slides public, and AISC can post them in the Steel Solutions Center or some other appropriate place so you too can have them. Now I've asked him in front of everyone, so he has to say yes. All right. Next, we're going to use Excel. It takes no more complicated software than that. And Excel has a very nice function in it built into the program called lognorm.dist. And it allows you to play a variety of games with log normal distributions. And you can use it to estimate what the mean value, not the actual value, but what the mean value of demand capacity ratio is for the distribution of demand and material resistance that you're dealing with. You can use that same function then, knowing that mean value, knowing your dispersion, and knowing your demand capacity ratio to find out what your annual probability of failure is. So for those of you not familiar with log normal distributions, I'll just give you a little bit of an introduction here. A log normal distribution is a lot like a normal distribution. The normal distribution is the famous even bell curve that you've seen millions of times in millions of places. The difference between a log normal distribution and a normal distribution is for a log normal distribution, it would look like a normal distribution if you plotted it in log space. All right? So if you look at the x-axis here, you can see that it's skewed off to the right. It's almost a bell-shaped curve, but it's skewed off to the right. If you were to plot this probability distribution in terms of the log of the value of x rather than the value of x, it would look normally distributed. It would be a perfect bell-shaped curve. Now, we tend to use this type of distribution a lot in structural reliability analysis, and there's a couple of good reasons for that. One of them is a normal distribution, which is easier to use, has tails on it, as does this distribution, but the tail on the left-hand side of the distribution runs into negative negative territory. And what that means is if you were using a normal distribution to represent your probability of failure, and your x value was, for example, demand capacity ratio, that would tell you that you have a non-zero probability of failure when you have zero load, or even if you have negative load, which doesn't make a lot of sense. The log normal distribution has the nice property that it never has a positive value below zero. At zero, the probability of failure is zero, which is nice. The other thing is that the form of this distribution, with the skew being off to the right that you see here at larger values, tends to match natural behavior, not identically, but pretty well. For example, steel mills shipping steel out to the industry. They take mill cert reports, right? If they're producing a grade of steel that's supposed to have a 50 KSI minimum yield strength, and they pull a mill cert on the heat, and it's 48 KSI, they throw that heat back into the kiln, and they remelt it, and they realloy it, and it comes back out having a higher yield strength. But for many of our steel specifications, there's not an upper limit on the upper value of yield strength, and so you actually get a skewed distribution that looks something like this. All right, so how you characterize a log normal distribution is with a median value. And what's important about the median value, it's not the average, the median value is that value that has a 50% probability of being exceeded, which for a skewed distribution is not the average. The standard deviation in log space is the other thing that we measure to measure the amount of spread of that distribution. And you can think of that as being equal to the coefficient of variation, something that you're more familiar with. The Excel lognorm.dist tool. You put it into your spreadsheet just like this. X is the value, in our case, the demand capacity ratio, at which you're interested in finding the probability of failure for. Mean, now Excel is somewhat confusing here. When Excel says mean, what they're really looking for is the log of the median value. That's the trickiest thing about using this. So keep it in mind that if you're using this function, where it says mean, think log of median value. The standard deviation that it asks for, they're really looking for the coefficient of variation. I don't know why Microsoft does this, but they do. And then you have a choice of true or false. You do true if you want a cumulative distribution and know what the probability of exceedance is for a given value of DCR. And you use false if you want to do a probability density function, and that's of no use to us whatsoever. So don't do it. All right, where do we get these values of dispersion and load and resistance? Well, when Bruce Ellingwood had his summer camp back in 1977, he put together a publication which is available. It's NIB Special Publication 577 from the National Bureau of Standards, and it lays forward all of the dispersions in demand and resistance that they assumed in putting together the load combinations for ASCE7. And Ted Galambos has this very nice paper that you see here, where he gives you the important ones for steel structures. I also will give them to you. Now, Ted, when he looked at uncertainty in loading, or V sub Q, he divided that into two things. He divided it first into the actual uncertainty of loading and how many people and how much stuff someone might put in a room like we're sitting in today. And he calls that V sub L. And then the other, which he called V sub P and I call V sub M, relates to how well engineers can actually calculate what the effect of that loading is on a member, given that you tell them to use 40 PSF or 100 PSF. And he recognized that all of our calculations are approximate in some manner. Even if we're calculating the flexure in a simple beam, that simple beam may be attached to its supports using bolted shear plates, which actually have some fixity associated with them. So WL squared on 8 isn't the real number. And probably when we're calculating dead load, We neglect the fact that the concrete floor, when they poured it, sagged down a little bit in the middle and maybe a little bit heavier, have a little bit more concrete than we thought of. So that V sub M accounts for the ability of engineers to actually model and predict the effect of the loading they've been told to design for. And you get V sub Q, the variability in the load effect, as the square root of the sum of the squares of V sub L and V sub M. And that's given in this table on the left here. And it depends a lot on the type of load that you're looking at. For dead load, it's pretty small, about 10%. For wind load, it's pretty large, about 40%. For seismic effects, it's so large we pretend it doesn't exist because we can't deal with it. On the right-hand side, we have V sub M, which is how good are engineers at actually computing these things. And that's generally a pretty small number, meaning that we're pretty good at doing it. It's generally less than a 10% error. Now let's talk about dispersion and resistance and bias and resistance. What is this? All right, so this is some column data. Actually, it's the data that the AISC column formulas are based on. And it's showing as a function of L on R, or lambda, what the critical strength of the column is. And there's a curve fitted to it that looks very much like our column design curves. And in fact, there's a number of curves fitted to it. And what those number of curves are different curves that AISC has used over the years. And what you can see is that these curves tend to have bias on them. AISC doesn't want your columns failing. So they don't give you a median value, like my blue line here. They give you lower bound values. So our resistance has inherent bias built into it. And then you can see that some of the dots are above my median line there, and some of my dots are below the median line, and that's the dispersion or coefficient of variation. That exists for a variety of reasons. Maybe the yield strength of one element was larger than another. Maybe the load was supplied with slight eccentricity in one element and not another, etc. Ted very nicely gave us a table that tells us what the bias are inherent in the equations that we use to design various types of member, and also what the coefficient of variation is. All right, so this data is available. Now we want to use it to figure out if my beam that has a DCR is actually going to be safe when the DCR is 1.07. So I want to know, what is the annual probability of failure of my beam with a DCR of 1.07? From ASCE 7, table 1.3.1, I can find my probability of failure at a DCR of 1.0 as 3 times 10 to the minus fifth, just as I told you before. I can go into either that NIBS 577 document or to Ted Galambos' paper and find out what my variability in loading is. Now to do this, my beam is going to be subject to dead load and live load. And the variabilities are different for dead load than they are for live load. So when I calculate it, I have to consider the weighting of dead and live load in terms of how much of the total demand on my beam is a result of dead loading versus live loading. For my beam that I'm looking at in this example, it turns out the strength demand is 10% from dead load and 90% from live load. That's a sort of an extreme value. And we use this equation that you see here to calculate a composite variability on loading. And what we do is we take the weighting of dead load, 10%, we square it, we multiply it times the variability in dead load, which happens to be 10%. We add that with the weighting of live load, 90%, we square it, we multiply that by the variability in live load, 25%, and then we add on the professional variability or modeling variability of 9%. We square all of those things, we take the square root, and we find we have a combined variability of 25%. All right, now we want to find the dispersion and resistance. I find that it has a value of 0.12. Where did I get that from? Well, I go back to the table, and I look at a beam that's behaving elastically, and I find out that it's got a coefficient of variation of 12%. Find my total dispersion resistance and demand. It's the square root of the sum of the squares of the variabilities in resistance and demand. I calculate it as 0.28. Now I want to find the mean value of DCR. That's the DCR at which there's a 50% probability of failure, noting that when I have a demand capacity ratio of 1, my probability of failure is 3 times 10 to the minus fifth. And what I do is I go into Excel, I use the log norm.dist function, I use a coefficient of variation of 0.28. I know that when I have a demand capacity ratio of 1, I have a probability of failure of 0.03. And what I do is I go in and I use that log norm.dist function using different values of the assumed median and find out what the predicted probability of failure is at a DCR of 1.0. So I throw in a bunch of trial values, and I find out that with a DCR of 1, and I'm looking for a probability of failure of 3 times 10 to the minus fifth, my answer is going to be somewhere between 3 and 3.1 or so. So that's the mean value of the demand capacity ratio that the 3 times 10 to the minus fifth is based on. All right. Now I want to find the probability. I've defined my probability distribution. It has a mean value of 3.1 approximately. It has a dispersion of 0.2.8. I can use the log norm.dist function to find out what my probability of failure is for my beam with a DCR of 1.07. It turns out it's 7 times 10 to the minus fifth per year. Well, is this acceptable? We still have to make that decision. It's 2 times worse than desired by the code. But at 7 times 10 to the minus fifth, it's still not very likely to fail. So many engineers, knowing that, would say, that's something I can accept. By the way, I'm going to show you a graph here, and what this graph shows is that you can actually accept pretty large DCRs without affecting your probability of failure a whole lot. It's hard to see in this form. If you go to this form here, you can see that at a DCR of 1.2, you're still at less than 0.05% per year. And at a DCR of 1.3, you're still at a probability of failure of less than 0.1% per year. Gives you an understanding, perhaps, of how conservative our codes really are. Now, a warning about this, just so you don't think I'm telling you to go out and design your structures so that they all have DCRs of 1.2 and 1.3. I'm not doing that. If you design 100,000 beams and they each have a probability of failure of 0.1% per year, and the structures they're mounted in last 50 or 100 years, it's pretty probable during that time that one or more of those beams are going to have a failure. All right? So this is a game you might want to play occasionally, but not routinely. The answer about how reliable a member with a DCR greater than 1 is depends a lot on the anticipated length of service, the number of members that are affected. So you don't want to design your structure so that every floor beam or every connection of the floor beams has DCRs of 1.5 or so in it. And also your individual tolerance or your client's tolerance for risk. We can explore these things. We can look at, for example, at the effect of duration and say, well, our structure is going to be around for a lot of years. I'm not interested in a single annual probability of failure. I'm worried about the probability of failure while I'm still practicing and someone might sue me. Or maybe I'm worried about the probability of failure while the structure remains in service because I really don't want to kill anyone. So if you're interested in the probability, if you know the annual probability of failure, and you know the number of years of interest, n, you can compute what the probability of failure over that life is using this formula here. And it's going to be 1 minus the quantity 1 minus the annual probability of failure raised to the number of years of service that you're interested in. I've gone through and I've calculated that for various DCRs. And you can see that as you go to longer service lives, the probability of failure over that service life increases. And of course, as you go to higher and higher DCRs, the probability of having a failure increases. And I've said for my personal tolerance, I'm willing to tolerate a probability of failure of 1% over the service life of the structure for something that I may be engineer of record for. Probably you don't want to go more than that. Some of you may be willing to take larger risks than that. So I've shown here what types of DCRs I might be willing to accept on a one-off basis in one of my structures when I'm in that annoying situation where the load has gotten larger, or I'm evaluating an existing structure and I find an occasional member doesn't work when I check it to the spec. We can do the same sort of thing with earthquake loading, but we have a different table in ASCE 7 that we want to refer to. In ASCE 7, we find the reliability table tells us that for earthquake loading, if we have a risk category 2 structure, we're designing for not greater than a 10%, a lot larger, chance of failure, given that we experience maximum considered earthquake shaking. So we might ask a question, well, if the structure has a 10% chance of failure, if it sees maximum considered earthquake shaking, what is the probability of failure if it experiences design earthquake shaking? Your client might want to know, you might want to know. So we start with our known probability of failure, 10% in this case, just like we did before. We recognize that design earthquake shaking has a DCR, if you will, of 2/3, because the intensity of design earthquake shaking is 2/3 of that of maximum considered shaking. And we want to determine the probability of failure given that we experience design earthquake shaking, knowing that the probability of failure at maximum considered earthquake shaking is 10%, and I will tell you the coefficient of variation associated with this is 60%, and that's what the design ground shaking maps are based on, a coefficient of variation of 60%. So I go into my same spreadsheet. I want to find the median value of ground shaking with that COV of 0.6 to define my probability of distribution. And what I'm looking for is what value of the median ground shaking gets me a 10% probability of failure at the MCE. And I go in that I find that a value of about 2 or so produces a 10% probability of failure at MCE. Knowing that I have my probability distribution, I can use my Excel function to find out what my probability of failure at design earthquake shaking is, and I find out that it's 2.5%. You can do this to play other games as well. You can ask yourself, you can go through and do an evaluation of an existing structure and find out that this structure has half the strength that the code requires today because it was designed 20 years ago. What is the probability of failure of this structure? I can use that same distribution, plug in half as the ground shaking intensity, and find out that I now have a 21% probability of failure if I see design earthquake shaking. So, in summary, our structures are really safe. We design them with a really low probability of failure, except maybe for earthquake. The good news is our maximum considered earthquakes aren't supposed to happen very often, only once every couple of thousand years or so. LRFD was invented to provide a rational and consistent way to set margins of safety for structural design. LRFD was calibrated back to historic levels of safety accepted in ASD methods. Where did Ted and Bruce and the others come up with 3 times 10 to the minus fifth as an acceptable failure rate for a steel beam and flexure? They didn't pull that number out of the air. What they did is they designed a couple of steel beams using the then ASD procedures and AISC. They did a reliability study and they came up with a number of 3 times 10 to the minus fifth, approximately. And they said, I guess that's what we'll use because we don't want to make LRFD more oppressive on the profession than ASD was. We just want to be more consistent. For unusual design situations, if you understand it, LRFD can provide insight into how bad is and assist you in making decisions about whether or not you should scroll at the bottom of your calculations, say okay. One last thing, we did this very nice study for the Pentagon. We presented demand capacity ratios, we presented the probability of failure, and we said, you think it's acceptable? They were not willing to make that decision. So don't expect your clients to make that decision for you. That's something, unfortunately, you're going to have to take on. And when you take that on, someone, if something goes wrong, might call the question the judgment that you used in making that decision. So with that, I'll be happy to take questions from you. And again, I'll remind you that the PDH code is 24423. So any questions? Yes?
Do you have a paper related to this one?
Do I have not published a paper for this one? Sorry, the question was, have I written a paper describing this procedure? And the answer is no, I have not yet written a paper describing this procedure. I could probably be persuaded to do so. In the meantime, I do have these slides, which I will make available to anyone who wants them. Yes?
You said that we shouldn't expect our clients to make these decisions. Should they, though? I mean, should it fall only to structural engineers to make these decisions?
So the question was, I said, don't expect your clients to make this decision. And someone in attendance said, really, isn't it the client's job to make that decision? And I say, yes, it really is the client's job to make that decision. And some clients will make that decision, right? So you're in this situation. You've designed a structure. It's in construction. For whatever reason, they want to put more loading on a beam. You go through and you calculate not a DCR of 1.07, 1.3, right? It's going to cost a significant amount of money at this point to fix that beam because maybe now the finishes are in place. So they're going to have to do some demolition. It's going to delay the opening of the building. If you say the beam has to be strengthened, you're going to cost the client money, but you don't want to necessarily make that decision on their behalf. Some clients, if you go to them and say, well, you know, we understand you want to put more load here. It's going to cost $20,000. You figure out with the contractor to bring this back so that it works per the code. If we don't do it, you have a probability of failure of X percent over the life of the structure. Some owners will make that decision. Problem is, lives of structures are really hard to predict. We often say that we're designing structures for a 50-year life. If you walk around Baltimore, I think you'll find a lot of structures that are a lot older than 50 years. I know there's a lot of structures in my city that are a lot older than 50 years. Your warranty really doesn't expire if the structure survives beyond the 50 years, although probably we're not in practice anymore, so we might be safe. In the back of the room. So I think the question was, how do you convince a building official? Is that correct?
Yeah, how would you present your calculations or your
Yeah, so I would never take this to a building official, right? Because the building official's job is to enforce the code. And even if you're using the portion of the code that allows you to use alternative means and methods to demonstrate equivalence to the code, you're not equivalent. You're not as safe as the code, right? My little DCR of 1.07, I had twice the annual probability of failure that I would have if I had actually conformed to the code. So no building official, even if I explained it to him, is going to approve this, right? But how many times when you're in that situation, you've designed a structure, for whatever reason, someone wants to put more load on portions of it than you designed it for. You go through, you do this check, you come up with a DCR of 1.05 or 1.1 or something like that. How often do you go to the building official and ask them if it's okay? I never have in my 40 years. I just make the judgment one way or another.
I guess if you, let's say, so it would be harder to use it to have a milder fix, let's put it that
I'm sorry, I'm afraid I didn't hear that quite all.
If you were trying to use this methodology to make the fix less onerous, then I guess that really wouldn't work because you would have to go into a building official.
Yeah, so the question was, if you found yourself in a situation, more load on the structure, you calculate a DCR of 1.5. Well, there's a couple of different fixes I can do. I can fix it one way and practically get it to a DCR of 1.1, maybe because I have headroom limitations in the space, or I could do a really radical fix that costs a lot more and get it down to 1.0. In that case, you would probably have to take it to a building official because they might want to permit the change. Yeah, I probably wouldn't go there.
If you do route a paper, can you include the probability of connection design failure in addition to the main structural members?
And so the question was, if I do write a paper, can I include the probability of failure of connection design? And the answer is yes. The variabilities associated with connections are also available in the literature, so it's not a problem to do that. Yes?
Why wouldn't you say that this methodology is better suited for an institutional owner like the federal government, where you can't get a decision without being at risk?
So the question was, would I say that this methodology is better suited for an institutional owner like the government because you might be able to get someone to make a decision? And my answer to that is no, because people that work for the government have a name. It's called bureaucrats. And in fact, since the time of Julius Caesar, this is an editorial opinion, since the time of Julius Caesar, the one thing every bureaucrat has ever been worried about is that they would make a decision and something would go wrong and someone would blame them for that thing having gone wrong because they made the decision they did and they would get fired. Now, the fact is no bureaucrat has ever been fired for making a decision because no bureaucrat has ever made a decision because they're worried about that. So, no, in this case, we had a government client and they were completely unwilling to make the decision. I think a private client would be more willing to make the decision. But what I think the real use of this is to provide you some comfort when you're stuck in this situation. You're doing an evaluation, you find a DCR that's greater than 1. Do you recommend repair of that condition or not, right? If you don't recommend repair of that situation and there is a failure down the load for whatever reason, there's going to be someone that's going to be angry about that and they could sue you for that, all right? So if you're sued for that, you need to prove that you've conformed to an appropriate standard of care in our society. There's a couple of ways to do that. One way to do that would be to have your attorney hire a couple of friendly engineers who say, for 50 years I've been designing things and I routinely accept demand capacity ratios of 1.05. That should satisfy the standard of care. You're doing what the ordinary reasonable engineer would do in that situation, right? Of course, the people that are suing you might find a few engineers who are willing to say, no, the code says you're supposed to have a demand capacity ratio of 1. If you're deliberately, knowingly, knowledgeably violating the code is there to prevent such failures from occur, you did not act in a prudent manner, right? So I view this as something to give you guidance as to if you're put on the stand someday, having approved a member that has a DCR of 1.1 or 1.15, and the thing actually has failed, and someone is suing you as a result of that, as a way you might be able to justify that, well, I did what a prudent engineer would do. I thought about what the risks were involved. I looked at the probability of failure. The probability of failure was, in my opinion, suitably low.
The IBC or IEBC allows for 10% and 5% increase in lateral and gravity loads, respectively. What are your thoughts on that?
Okay. So the question was, the IBC, the IEBC, and other codes and standards set a magic limit of a demand capacity ratio of 1.1. If you're modifying a structure and as a result of that, the demand capacity ratio on some element goes up to 1.09, you're okay. No one's going to question what you're doing. If it's 1.11 and you submit it to the building official and they're picky, they may say you have to strengthen not only this element, but perhaps the entire structure to conform to the code. So what do I think about that? Well, let's go back. Well, let's go to this. So 1.1, if you have one element that exceeds 1.1 in a structure with a life of 30 years, there is a 0.3% chance over that life of that structure that it's going to fail. Sounds pretty small to me. On the other hand, if you have 100 of those elements, there's approximately a 3% chance that there'll be a failure somewhere in that structure. I think it is a pretty conservative limit, but they did have to pick an arbitrary limit somewhere. And it's not unreasonable given that when people do this, typically they're not applying it on a one-off basis to one element, but they're modifying a structure and a whole lot of elements are going to have DCRs that exceed 1. So it's not unreasonable.
Another question, this is an interesting one.
What does your errors and omissions insurance say about this approach?
The question was, what does my E&O carrier say about this approach? My E&O carrier does not know that I'm doing this. My E&O carrier probably also does not know that all engineers approve DCRs of 1.05 or less routinely, even when they're designing new structures, because they're trying to give their clients economical designs. My E&O carrier won't know this unless he needs to, which I hope never happens. One more.
Could this method be applied to allowable stress design?
Question is, could this method be applied to allowable stress design? I'll give the incorrect answer and say yes, because remember that load and resistance factor design was calibrated back to allowable stress design. So approximately allowable stress design, if done properly and done with the appropriate demand capacity ratios of 1.0 or less, it's going to provide reliabilities which are approximately the same. It's why the AISC specification allows you to do ASD as well as LRFD, because it's not creating a dangerous situation. So the answer is yes, but keep in mind that allowable stress design is not as consistent as LRFD in hitting these targets. So the reliabilities are going to be approximately the same, but not identically the same. Okay, well, thank you for your attention. I hope you enjoyed it, and I hope you can find it useful.